Hi, welcome to another session of Circuits and Networks. Today's class we are going to deal with resonance. What is resonance and how does resonance phenomena occurs in RLC series circuit? So the basics of resonance we are going to learn from RLC series circuit. When you throw back your attention at RL series circuit from our previous classes, we have seen that an input AC signal when it is given, current is traveling through this closed circuit and the voltage is divided across resistor, inductor and capacitor. In some texts, you can see the impedance is given instead of individual resistors, inductors and capacitors. So it indicates the combination of the real component with the reactive component. So anyhow, we have to concentrate on resonance phenomenon pertaining to RLC series circuit. So in our past classes, we have seen that whenever an RLC series circuit is considered and it is driven by an AC source, if inductive reactance dominates the capacitive reactance, the RLC circuit behaves as RL circuit, and if the capacitive reactance is dominating the inductive reactance, then RLC series circuit behaves as RC series circuit. And from that analysis, we have estimated the power factor, which could be calculated with the help of voltage triangle or impedance triangle or power triangle. We have to take the inputs from single phase AC circuit when they are applied to RLC series circuit, and then we are going to understand the exact concept of resonance. So if at all you want to define resonance, a circuit is said to be in resonance if the voltage across the circuit is in phase with the current passing through it. This indicates that at resonance, the circuit behaves purely as resistive in nature. So the net reactance in that case should be zero because the voltage and current are said to be in phase, and that happens only in a pure resistive network. Or you can also define resonance in a circuit in which inductive effect and the capacitive effect neutralizes each other. Means what? It should be free from the reactive component. Or resonance is defined as a circuit having unity power factor. It indicates that the impedance of the circuit becomes purely resistive. So the impedance is only resistive, don't have the reactance component. Also, resonance is defined as a circuit in which input voltage and input current are said to be in phase, what we have seen from the previous definition. So all these cases match with the resonance concept. So there should not be any phase delay between the current and voltage when you're talking about resonance. So if at all resonance has to be defined in that way, then let us estimate the impedance because it has to be purely defined in terms of pure resistance. When you are going to apply this input to the series RLC circuit, you can estimate the impedance as the combination of the real component as well as the reactance component. What we have to make? We have to make impedance equivalent to resistance. Therefore, this terminal has to be made equivalent to 0. Then only we are going to obtain the voltage in phase with current. Thus, in a pure resistor, the voltage and current are said to be in phase. Then only the resonance will occur. So in order to occur the resonance phenomena, the voltage across inductor should neutralize with the voltage across capacitor. This indicates that the inductive reactance should be equivalent to the capacitive reactance, or we change this XL to omega L and XC to 1 by omega C. Therefore, we are going to get the value of omega naught, which we call as the angular resonant frequency, which is equal to under root of LC, 1 by LC. So if that is true, you can change this angular frequency to the normal frequency, and hence this is called as resonant frequency, which is equal to 1 by 2 pi under root LC. So here the units will be in radians per second, and F naught is treated as resonant frequency when the resonance occurs. So with the help of the impedance of the series RLC network, if we fix the resistor, inductor and capacitor values like some constant values and just change the range of frequencies, say F is equal to 10, 20, 30. When f is changed from 20 to 150, the angular frequency will also change from 10 to 150. And the observations that we can make by substituting the values of f in the impedance equation, we are going to obtain the result as resistance, which is going to become unchanged with the change in frequency. This is one observation. Another observation, inductive reactance will be directly proportional to the change in frequency. You can see Z is equal to R plus J XL. So XL and Z are said to be directly proportional to each other. So the frequency is changed, then naturally the inductive reactance will change, and it is indicated that it will be a linear value. So that is why it is proportional to frequency. And if you take the capacitance, the capacitive reactance will be inversely proportional to frequency because there is a minus sign over here. So with this analysis, if at all you plot the graph of impedance individually with RLC parameters by changing the value of frequency, this is what you're going to get. So you have a straight line, which is the resistance value because there is no change. Some magnitude of resistance, say resistance is equal to 5 ohms. If that is the value of resistance, then with changing frequency there is no alterations in the magnitude of resistance, so a constant line you can see in this fashion. Whereas this omega L, you can see it is changing with linearly changed value of frequency. So that is a straight line passing to the origin, and you can see there is a drop in the capacitance. You change the value of frequency, substitute the value of capacitance, some constant value, and you observe the alterations. You can see that the total impedance, when it is taken in terms of capacitive reactance, it gets decreased. So in many textbooks or in many literatures, you can see this is how the impedance graphs look like. When the resonance occurs, the total impedance of the circuit, it is observed to be like this fashion. It is quite similar to linear curve. It is decreasing at one point, and from another point it is increasing. So this decrease is because of capacitive nature, this increase is because of inductive nature, and exactly at omega naught, where we call as the angular resonant frequency, the resonance occurs. So that is equivalent to R. So this is how we have obtained the graph for impedance under change value of frequencies. So let us understand this graph in detail. What we got is the kind of curve in this fashion, where you have frequency which is known as resonant frequency, where the resonance is occurring, and the impedance is obtained to be the equivalent to R value. So this we can treat as the minimum value of resistance that can be obtained for RLC series circuit applied to AC. When you take the help of Ohm's law, you will obtain the value of current, because the impedance, which is equivalent to resistance, it is minimum, and the current is going to be obtained as maximum. So naturally the current graph will be quite opposite to the impedance graph. So this is how you are going to get the current graph. And so in many texts or in many literatures, you can see this is how we got the curve for current, because the current is inversely proportional to the impedance according to Ohm's law. So this is how we get the graph for current as well as impedance under resonance. The maximum value could be V by R. R is the value of minimum impedance. So this could be the maximum value of current, where you are going to get the maximum value at resonant frequency. So what we have to note, that the power factor is unity at F is equal to F naught, because it is purely resistive in nature. When purely resistive in nature, the RLC circuit, you don't have lead or lag conditions. So we are going to obtain a unity power factor under resonance. And power factor becomes lagging under inductive reactance, that is the frequency when it is greater than F naught. So here you are going to get the inductive nature. So this part from F naught to T, the curve, it will give, it is obtained because of the inductive reactance. And similarly, power factor becomes leading under capacitive reactance, which is quite obvious because before F0, the circuit is completely predominated by capacitor. So this is under impedance curve and this is under current curve. So this is how we are going to get. It is better if at all you make a tabular column for these passive elements RLC with the changed value of angular frequencies. With the help of natural frequencies, you can obtain the angular frequencies. So at resonance, that is at omega is equal to omega naught or F is equal to F naught, you're going to get the phase angle as 0. Therefore, power factor will be unity power factor. And after F naught, it will be lagging because the circuit behaves as inductive nature, and leading, that is before F naught, that is omega less than omega naught, the circuit behaves as capacitive reactance circuit. So this is how you can remember the concept of resonance. So let us frame F1 and F2, which can be obtained. You can see this point and this point, they are quite repeated at one kind of magnitude, and that magnitude of current we are going to obtain as the half of the current values of the maximum output. So this is treated also as half of the powers which you are going to obtain. So just in order to differentiate a lower frequency and upper frequency, we have estimated exactly at the division of this point, and this point will be determining the bandwidth where you can reach from one station and you can leave the one station. For example, if at all you will see in radio signals whether the signal is 92.5 or 93.5, they will indicate the station for radio where you can listen to the clarity of speech. And when you just enter to the bandwidth of the region, you can just hear the noise or fuzziness in the signal. So before entering to the station and after leaving the station, wherever you can go through the disturbance, that disturbance from the starting point to the ending point, we can treat as the receiving and terminating points of the stations. So that is can be treated as a bandwidth. We understand this bandwidth concept as the difference of the two frequencies, the upper frequency and the lower frequency. Okay, it can be defined as, from this curve, it can be defined as the difference of the frequencies where you can hear the noise of the station. You take any radio station where you are going to tune the radio, the starting point where you can just hear the signal in the name of speech or in the name of voice, and you can same feel the feel when you are going to tune from that particular station to the next station when you are traveling, the disturbance which you are going to hear. So this period of disturbance from the starting to ending, in order to arrive exactly at resonance where you have the clarity of speech, that particular point where the resonance is occurring, there we can hear the exact speech or exact the tuning where it is happening, where the clarity of the power which is going to be generated at the receiving station, that is going to be heard at the which has generated this sending station, it can be here at the receiving station only at F0. So that particular concept is the concept of resonance, where the clarity of speech is heard in a properly. There we can say that the power, whatever it is generated, it is 100% distributed to the receiving end. So if that happens at only exactly at a resonance. So for this series RLC circuit, it is defined, the bandwidth is defined as a range of frequency for which the current delivered to resistance is greater than or equal to the half of the current delivered to it. So from F1 to F2, you can set a bandwidth. Or in this case, the frequency at which the current response will be 70.7% or 1 by root 2 times of the maximum value is known as the bandwidth of the circuit. So this is how the telecommunication field is dependent upon the concept of resonance. So application point of view, you can take the telecommunication is the main applications of the bandwidth under resonance. So we have to find out the bandwidth value. So we have the current, which is nothing but the voltage supplied to the impedance value, the magnitude of the impedance. You have to take the values of XL, XC. And what is the maximum current? Maximum current we got in two times, at lower frequency and at upper frequency, that is I max by root 2. But I max is what? I max is nothing but again voltage by resistance times root 2 repeated twice, which is equivalent to the total current. So you can nullify these voltage values and we are going to get the equations for the passive component, which is generally obtained as omega L minus 1 by omega C plus or minus R equal to 0. So this can be framed as a normal equation of ax square plus bx plus c. So we can get the roots for this particular equation. So for this particular equation, how we are going to obtain the roots? We can obtain the roots as x is equal to minus b plus or minus under root of b square minus 4ac by 2a. Just substitute the values of b, a, and c. So when I'm going to substitute these values, this is what I can do. I'm going to obtain the value of omega to be r by l plus or minus under root of r square by l square plus 4 by lc whole divided by 2. So if at all you reframe this equation, we can going to get the second equation as a root equation, and compared to this value, that is r square by 4 rl square, for low values of resistors, this term can be neglected. When you are going to neglect this term, we are going to get the above equation as omega equal to plus or minus r by 2l plus or minus under root of 1 by lc. This we have treated already as resonant angular frequency. So if we substitute the resonant angular frequency in this equation 3, we are going to get the actual frequency, which is equal to plus or minus r by 2l plus resonant frequency. So I can get the value of lower cutoff frequency and upper cutoff frequency from this equation 4. So lower cutoff frequency or the lower cutoff angular frequency is obtained as omega naught minus r by 2l, and upper angular cutoff frequency as omega naught plus r by 2l. So natural frequency f1 and f2 can be obtained as equation 7 and 8. And we have already stated the bandwidth as a difference of the two frequencies, the upper cutoff frequency minus the lower cutoff frequency. So if you substitute equation 6 and 5 respectively in these two values, you're going to get the value of bandwidth as r by l. And if at all you substitute equation 8 and 7 respectively in f2 and f1, we are going to get the value of bandwidth as r by 2 pi l. So this we can treat it as equation 10. So once we have done with bandwidth, let us calculate the quality factor. How to define a quality factor? It is defined as the ratio of the voltage across the inductor or capacitor to the voltage measured at resonance. So you can take this quality factor to be VL to be the resonance voltage. Since it's the inductive reactance, if you consider, this becomes I naught x L naught by I naught R. This I naught goes off, so it becomes the ratio of reactive inductive reactance to the resistor. So when you substitute the value of inductive reactance, this is how we are going to get the equation for quality factor. And if at all you substitute the value of capacitive reactance, this is how you are going to get the quality factor. But omega naught we have already seen as the angular resonant frequency. You substitute the value of angular resonant frequency, then we are going to obtain the value of quality factor as 1 by R to under root of ratio of L by C. So these are the important parameters of resonance under series circuit: bandwidth, quality factor, upper cutoff frequency, lower cutoff frequency. If at all you concentrate on these parameters, then you can solve any problem related to RLC series circuit applied to AC. So in the next class, we are going to see some numericals on resonance, especially connected to series circuit and applied to AC parameter. And in the next class, we are going to see the resonance phenomena in parallel circuit also. So in today's class, we have dealt with resonance pertaining to RLC series circuit. I hope you like my video. Please share among your friends, subscribe to my channel, and please press the bell icon for the future notifications. Thank you.